Welcome you all to another lecture on strain energy principles. In today's lecture, we are going to see about the virtual work concept with an example. Okay, so before going into the virtual work method, that is principle of virtual work method, we'll first go through what is called as virtual work and what is the principle states. Virtual is something which is not real, that is imaginary or something which is assumed. Here we imagine a very small displacement that could happen, but without breaking the support or the connections or join something. So virtual means something which is not real or which is assumed or imaginary thing. The principle of virtual work states that when a body or a structure is in equilibrium, that is when it is already balanced, the total virtual work done by all the external forces during any small compatible virtual displacement is zero. That is, when a body is in equilibrium, there will be very tiny movement. So the force which tries to move the body and the force which tries to resist the movement will be balanced, will be equal. So there will not be any work done. So the total work done will be zero since both are balanced. Okay, so this is the principle of virtual work. There is a total virtual work done when there is a very small compatible virtual displacement. The total work done is zero. And here we take something called as external virtual work and internal work. The external virtual work is the work done by the external forces when a structure is given an imaginary displacement. Already we know that work done is force into displacement, and here the external virtual work is force into, and the imaginary displacement is taken as delta. So the external virtual work will be P into delta. And next, what is internal virtual work? When a structure deforms, so when a body or a structure is subjected to any kind of deformation, some internal forces will be developed inside the member. These internal forces, what they will do, they will try to resist the deformation and they will do the work internally. We have seen in the first lecture about how the strain energy is stored with an example, with an bow and arrow example. In that bow and arrow example, we just pull out the string. So what happens? The bow deforms. So due to the deformation, there will be some intermolecular rearrangement and they store some energy, and that energy is only released and the arrow moves out of it. So the same thing, whenever there is some deformation, some internal stresses or internal forces will be developed inside and they do the work internally. In case of truss, the deformation may happen due to stretching of the members. In case of beam, it will be due to bending. And they store this energy, and that stored energy is called as strain energy. The idea is that when a structure is in equilibrium, the work done by the external force will be always equal to the work which is absorbed internally. That is, the external virtual work will be equal to the internal virtual work. Everything is balanced. So energy is always balanced, nothing is lost. This is the main concept of virtual work. And here, what do we do in virtual work method? We just to know the displacement, we do not know the displacement directly. To determine the displacement, what we do, we just apply a unit virtual load, that is 1 kilonewton load, that is a unit load we apply at the point where we need the displacement. So what happens, this will create some internal forces, that is virtual forces, because we are applying just a unit load. This virtual forces should be combined with the real forces. using this trick, we determine the displacement mathematically. So just to determine the displacement, we apply a unit load at the point where we need the displacement. Using that load, we are combining it with the real force which is actually acting there, and using this we are finding out the displacement. Okay. The principle of virtual work method is applicable for both truss as well as beam. In case of truss, the external work will be always load into displacement or the deflection or the deformation. Here the external work is unit load, because externally we are applying a unit load, that unit load into joint displacement in case of truss. What will be the internal work in case of truss? There will be stretching. So the internal work will be due to stretching of each member. And what does the principle of virtual work states? External virtual work is equal to internal virtual work. So 1 into delta, which is equal to, this is the internal work, which is N into N L by AE. Here you can see delta is the displacement at the joint where it is required. And this small n is the axial force in the member due to the unit load, that is the virtual load what we apply. And capital N is the axial force due to the real loads, that is what is actually applied in the member. And L is the length of the member, cross-sectional area, and E is Young's modulus. This is in case of truss. In case of beam, the external work is unit load into deflection. Okay, and the internal work in case of beam, what happens? Beam just bends. So there will be bending of beam. And the external work, which is 1 into delta, which is equal to the internal work, which is integral of m by E into dx. This small m is due to the, it is a bending moment due to unit load. And this capital M is due to the real load, bending moment due to the real load. So this is how we will be finding out the deflection using virtual work method in case of truss as well as in beam. Here is an example for the principle of virtual work, that is for calculating deflection using virtual work method. Okay, so a simply supported beam is given. At point C, 60 kilonewton load is applied. We are asked to find out the deflection at point D, and Young's modulus is given as 2 into 10 to the power of 5 Newton per mm square. Moment of inertia is given as 4 into 10 to the power of 7 mm power 4. Just here convert into the unit, everything should be same, all the units should be same. So since here all the distances are given in meters, we are converting it into meters. So E will be 2 into 10 to the power of 11 Newton per meter square, and I is 4 into 10 to the power of minus 5 meter power 4. In case of beam, this is the formula to find out deflection, that is integral 0 to L m into m by EI into dx. Okay, so first we will find out the real bending moment, and then we also find out the virtual bending moment. So to find out real bending moment, we have to take the load which is actually applied on the beam. Here the load applied is 60 kilonewton, which is applied at point C. So we are taking moment about point A. What will be moment about point A? It will be RB into this distance, which is 6, minus 6 into 2, which is equal to 0. So from here we are finding out RB. The next, applying the next equilibrium condition, which is summation of vertical force is equal to 0. RA plus RB will be equal to 60. From here RA is 40. Here we are splitting up the total beam into 3 sections. One is A to C, next one is CD, and the next one is DB. For the first section, the limit is 0 to 2. So in between this A and C, take some, consider a section which is at x distance from A. So MAC will be RA into x. RA is 40, 40 into x. Similarly, between C and D, take a section which is at x distance from A and see to that the distance of the section what you are taking should be from any of the support. You should not take the distance from in between, that is from C you should not take the distance x. It should be from any of the ends. So here we are taking from A the distance as x. That is, we have a beam. This is point C. This is point D. We are taking a section in between which is x meter from A. What will be the bending moment in MCD? RA into x, and here at C we have a, at C point we have a load 60, and this distance will be, this distance is 2 meter. So the distance between the load and this section what we have taken here is x minus 2. RA into x minus 60 into x minus 2. Substituting the value of RA, we'll get minus 20x plus 120. The next, the third section is from 0 to 3. We are taking this from, we are taking a section here which is x meter from B, and MdB will be RB into x, which is 20x. This is for a real bending moment. And now we need deflection at point D. So what we have to do, we have to apply a unit load or an imaginary load at point D. We are applying a unit load at point D. For this virtual load, we have to find out the bending moment. Same way, taking moment about point A, RB into 6 minus 1 into, the distance is 3. From here, RB is 0.5. Same way, RA is also 0.5. Because the next one is summation of vertical force is equal to 0. So if we take summation of vertical force as 0, what will be there? RA plus RB will be equal to 1. Since RB is 0.5, RA will also be 0.5. Next we are taking the virtual bending moment. First one is, we are taking a section 0 to 2 meter. So MAC will be RA into x, which is 0.5 into x. Next we are taking CD portion. We are taking a section in CD portion. Here also it will be RA into x. We have to take x meter from A. And the third portion is 0 to 3. Here we are taking a section between somewhere between B and D, which is at x meter from B. So that will be RB into x, which is also 0.5x. Then apply all the values in the formula, deflection formula, which is integral 0 to L capital M small m divided by EI into dx. Capital M is due to the real moment and small m is due to the virtual moment. That is the moment due to virtual load divided by EI into dx. Multiply it, simplify, then integrate, apply the limits. The first one is, the limit is 0 to 2. You can apply only the upper limit. Since the lower limit is 0, you can neglect it. With the second term, you have both lower limit as well as upper limit. So first apply the upper limit, then minus lower limit. Third portion, the lower limit is 0. So we can apply only the upper limit. And delta will be 28.7 mm. After this step, you have to apply the value for E and I, which is already given in the problem. Substitute the values and the deflection will be 28.7 mm. Thank you.